So, welcome to the next important topic, which is on quality control. Till now we were been discussing about how to draw a part, then after drawing a part how do you manufacture, then we were looking into process plan. So, now it is getting into a new field which is called as quality control. Again here, if you wanted to establish a SIMS environment in a factory, you are supposed to have a good quality control over your product, and you should try to store the data using a computer. So, earlier the quality control was talked about only in terms of product performance. Now, we are trying to talk about which day it was manufactured, who manufactured, how was it transported from one place to the other, what is the service condition it is expected to do. All these things are now getting tracked. In fact, today there is a new theme which is talked about in auto industry. They are saying that you try to get my car on lease, and we will try to maintain as well as assess the quality of the car regularly and then try to do maintenance for your car. So, rather than owning, they are trying to give it on lease, which plain industry it is very common. Now, they have slowly started doing it for high cost cars also. So, quality control is becoming very important. What was done earlier manually, now it is going to be done by the use of a computer, and when it is computer used, then the data which is digitally stamped is stored in records. So, now this is the next topic of our discussion, computer aided quality control. So, in this topic or in this lecture, we will see the following content. The first one is going to be computer aided quality control. We will see the definition. Then we will try to see inspection metrology. So, then we will see conventional measurement and gauge techniques. Then we will discuss about coordinate measuring machine, which is exhaustively used. Then we will try to look into surface measurements, machine vision, then optical inspection techniques, then non-contact, non-optical inspection techniques, and finally, we will see some amount of control chart in this lecture. So, computer aided quality control is the engineering application of computers and computer controlled machines for the definition and inspection of the quality of the product, which includes measuring equipment management, goods inward inspection, what came inside in input. See, currently it is pretty interesting. You have a machine, you have an input, you have an output, right. So, when the output is good, everything is good. When the output is bad, so we just go back and then look into the machine. If the machine is all right, many a times what we do is we will say that okay, there is nothing wrong, it is because of chance this has happened, and we go. But it is also worthwhile to check the input raw material which comes inside, what is its consistency of the product when it is given to the machine, and then what is the output. Okay. So, goods inward inspection is also very important. What is the batch size inspection you did and what is their outcome. So, this is also measured goods inward inspection. Next is vendor rating, which is very important. I have supplied 10 items to you, 10 same items to you over a period of last 1 year. What is the performance of those parts which I have given to you for machining and then to a supplier. So, that is called as vendor rating. How perfect I am, what is the scrap which I produce, and how much are in the marginal good and bad. So, with that we give a vendor rating. Then attribute charts, then SPC, statistical process control charts we look into, and finally documentation. All these things are getting into the information of computer aided quality control. Because of computer existence, all these data can be fitted inside, and that can move along with the parts when it is moving from factory to factory, from assembly station to the final station everywhere. So, this is a very important advancement which has happened, and this makes the SIMS environment more successful. Earlier, quality was thought of after making a part, checking for quality. Now it is thought of while making a part, checking for the quality. So, not even the first part will be scrapped today. So, this is the definition for quality, computer aided quality control. Computer aided quality control is the engineering application of computers and computer controlled machines for the definition and inspection of the quality of the product. So, if you put it in a schematic diagram, so or a block diagram, it looks like computer aided quality control gets following information: product identification, process identification, parameters to be tested, upper and lower specification for producing a attribute of a part. Then what is the quality standards? For example, ISO, QS, all these things are BIS. These are some of the standards. Then government standards, test programs, test procedure, how to do the. So, for example, when you have to measure the thermal conductivity of a material, we should try to follow a certain procedure, establish it to a normal temperature and then measure it. So, test procedure is very important. When we are trying to measure the temperature induced phenomena on the expansion, linear expansion, the test condition has to be at room atmosphere, and they have put certain parameters. So, that is called as a test procedure, how it has to be done while using a measuring device. Abe's principle has to be followed. So, all these things are put in the test procedure. Then algorithms to evaluate the test data. For example, I have a flat plate. If I want to measure the flatness of this plate, so naturally I have to take all the data point, discrete data points all across the flat surface. So, then I get the data. Now, what do I do is I try to put the data and try to generate a surface. Now, I am just drawing the 2D. So, the variation in this, if I project it on a 3D, is called as a flatness. So, the algorithm for getting out individual data and constructing from the point cloud data a surface, that is called the algorithm to evaluate the test procedure. The test results and product acceptance, rejection levels, then quality trends, quality history, cost of quality control and process performance. One interesting data which people have been telling is in Europe, on Friday evening the quality of the cars produced and the Monday morning the quality of the cars produced are not up to their expectation. That means to say there is always a human error happening because of weekend effect and weekend hangover. So, it is a data which is generated, and now what people are trying to do is they are trying to balance it. People who go on a Friday who is working on car assembly and who come on Monday morning car assembly, they are trying to be more conscious about on all the assemblies. And the other option is the company has started doing it in two phase. That means to say one part of the industry people will come on Tuesday to Saturday and the other one will come from Monday to Friday. So, they try to balance the load and do the operations. This is all from the quality history. Then the cost of quality control. So, cost of quality control is from the rejection, refurbishment, what is the cost involved to generate a quality product, and process performance. All these things are inputs which are given to computer aided quality control. So, how does this happen is, first we will have a CAD. From a CAD it is attached to computer aided drafting and documentation. Okay. From there the data goes to computer aided process planning. Okay. From the process planning it goes to a process planning. Then from there, here you have a drafting, this goes to process planning. Okay. So, when I talk about CAD, we talk about product concept and then design engineering. Okay. And from design engineering, it goes to drafting. So, this product concept comes from customers and market. This here we talk about the QC, quality control, and here comes computer aided quality control. Look at it, how holistically it is all getting built. From the process plan, what you get is order, new equipment and tools. Okay. So, then from it goes to a production schedule, and from production schedule it gets to production. So, from the quality control, for production we try to have a computer control. So, we will have material handling, machines and material handling we will have, okay, etc. So, this goes here. So, the quality control from here to production it goes, and it also gets the information back and forth. So, it goes between these two, and this is the data which flows from here to here. So, if you see, this is a overall holistic view of the complete industry, and you can see where does CAQC come into action. So, CAD can be split into product concept and design engineering. Design engineering leads to drafting, and drafting the information goes to PP. So, PP is process planning, and process planning also computer aided process planning comes here and it helps it. So, from here we try to see whether there is a need for ordering new machines or old machines, then a production schedule is done, production happens. In production we will have machines and machine tools. So, all these things try to give an input to computer aided quality control, and this in turn gives to quality control. The quality control in turn gives the opinion to customer, it goes to customer and the cycle gets completed. This is a very important block diagram which you should understand, which talks in totality everything which happens inside a SIMS environment. Now, let us see what is inspection metrology, which is very much talked about. First, we will try to understand what is measurement. Measurement is a procedure in which an unknown quantity is compared to a known standard using an accepted and consistent system of units. Very interesting, you see here, unknown quantity has to be measured, and how do you measure it? You compare against a standard and then using a accepted and a consistent system. How many keywords? So, known unknown quantity compared with a standard accepted consistent system of units. The means by which the inspection by variables is accomplished. Metrology is nothing but a science of measurement. Concerned with 7 basic quantities, we measure length, mass, electric current, temperature, luminescence, intensity, time and matter. These are the 7 basic quantities which are measured. The science of measurement is nothing but metrology. So, this metrology goes here. So, that is inspection metrology. From these basic quantities, other physical quantities can be derived. These are the 7, but many things can be derived from this 7. So, the most interesting thing which we always do is length measurement, mass measurement, and today exhaustively electric currents are measured, temperature, time and the matter is measured. When we talk about inspection metrology, so inspection metrology, we have a interactive program. And we have a NC programming. So, here inspection program is given, and here there is a inspection which is done by a robo or by a machine or robo. Okay. So, this program okay. So, we will have a machined part. Okay. So, from NC program what you get is G codes, and this goes to a milling machine, okay, and this is the which is lead to the part. So, this is what is a thing. You will have an interactive programming. From the interactive programming you get an NC program. So, when the same you also try to get a NC program as well as an inspection program. So, NC program is given to a milling machine to produce a part. So, then the program tries to tell you what all this fellow has machined, those points, critical points to be measured, and the measurement will be done by a robo. So, this is a separate vertical and this is a separate vertical. This clearly says that how is the interaction happening between the program and the NC program what you generate. The characteristics of measuring instruments, first is accuracy. We have seen accuracy and resolution in robotics, we have seen in CNC. A quick recap of the same. Accuracy, how closely the measured value agrees with the true value is called as accuracy. Then resolution, the smallest variation of the variable that can be detected is called resolution. Between these two you have one more terminology which is called as precision. A measure of the repeatability of the measured process is called precision. Generally a rule of 10 is used. The measuring instrument must be 10 times more precise than the specific tolerance. For example, you say 6 plus or minus 1 millimeter is the tolerance you are giving. The measuring device must have 0.1 millimeter as the precision should be there for the measuring device. Okay. So, the speed of response, how long the instrument takes to measure the variable is called as the speed of response. You might have a data measured, at what time it comes to a computer and how does the data get transferred, the time involved. The other thing is when we talk about others, the operating range, reliability and cost are the other important characteristics which are there for a measuring equipment. Accuracy, precision, resolution, speed, operating range, reliability and cost. These are the 7 most important characteristics of a measuring instrument. So, this is with a large variance, the mean is here, this is a true value, this is the large variance you have, and distribution of measurement you can have it like this, and then here you have the same large variance is a small variance, the mean is still there. So, the true value is here, the mean is here, and the next one is the true value is here, the mean is around. So, it is measured variable. So, you can see, so this is of a high accuracy, low precision. Next one is low accuracy, but high precision, because it is all getting repeated at the same point. So, here if you have a systemic error, you can shift it, and the last one is high accuracy and high precision. The mean and the distribution variance are very close by. So, here it is of low precision, this is of high precision, low precision and high precision. So, there are two types of instruments which are generally used for measurement. One is called as analogous, the other one is called as digital. There is a mixed opinion. People say all analogous instruments should be converted into digital and we start using the data, but now people say that digital puts a restriction on increasing the resolution more. So, now it is better to have analogous data rather than to have digital instruments. So, there is a mixed opinion. So, we can choose depending upon the requirements, we can choose either an analogous equipment or a digital instrument. Analogous measure instruments are output signal varies continuously with the variable being measured. So, for example, when you take a sinusoidal voltage, this is the time period, this is the voltage. So, you can see here it varies with respect to time. And now, the same thing if it has to be digitized. So, what we do is we try to digitize at this point. So, here you see that it is all digitized. So, you will have a voltage, once it shifts this time you will go to this. So, next is high standard, next high standard, next high standard it will go. So, can assume any of the discrete numbers of incremental values corresponding to the variable being measured is called as digital measured equipment. So, the advantage of analogous is output signal can take on any of an infinite number of possible values over its operating range. If you want to split it to a smallest level, you can keep splitting if you have a analogous data. Reconstructing from a digital data to an analogous data will always have some error. So, that is why people say digital has a restriction. Earlier people used to convert from here to here, now people are going from here to here. So, here number of possible outputs is finite, here it is infinite. So, it is finite. The advantages is it is easy to read the equipment and easy to interface to a computer because it is a digital value. There are two basic types of inspection techniques, one is contact, the other one is non-contact. Wherever there is a soft material and wherever there is a complex geometry, we try to go for non-contact inspection. Contact inspection makes contact the measuring device with the object being inspected. The instrument and object touches. Here instrument and object no touch or it does not touch. So, what can we use? We can use light, electromagnetic field, proximity sensors can be used, light can be used, we can use pressure and so on. So, in non-contact type does not make contact with the object being inspected. This is generally preferred for soft and complex geometries. So, contact inspection techniques uses a mechanical probe that makes contact with the object being measured or gauged. The principal technique are conventional measuring and gauging instruments. Gauges. Gauges are only used for mass production and they are generally used to have a relative comparison. They will not give you the absolute value. Absolute value cannot be there. It will just measure and say okay, the deviation, it falls within the deviation, you are getting it. So, conventional measuring and gauging instruments, manual and automatic, all these things fall in this technique. The coordinate measuring machine is a part of a contact measuring machine. Today you have also non-contact type coordinate measuring machines, where in which we use exhaustively optical. Then stylus type surface texturing machines are the other thing. So, the three principal techniques are conventional measurements, coordinate measuring machine and stylus measurement. So, the difference between coordinate measuring machine and stylus is here it is continuous data we get, here it is discrete data we get by using the same contact probe. We touch and then get it. So, when you talk about non-contact inspection techniques, use a sensor or a probe located a certain distance away from the object being measured or gauged. So, two categories, one is optical, uses light to accomplish the inspection, non-contact uses energy form other than light. So, the advantages of non-contact inspection is avoid possible damage of surface objects. That is what I said, soft materials, it can be skin, it can be rubber, it can be PDMS, whatever it is. Inherently faster than contact, of course, yes, it is fast because it is going to scribe over and then go, it will not going to touch. So, it will just move across it. Can often be accomplished in production without additional part handling, and then increase opportunity of 100% inspection. So, all these things are possible in non-contact. Today, because of this advantage, non-contact inspection is gaining more importance in a factory environment. When we try to put PQ chart for inspection technique, this is P and this is Q. This P is part variety and Q is part quantity. So, here if you see manually measuring and gauges, wherein which we use human oriented work is done here. So, here a human being is exhaustively used in measuring. Okay. Next, if we slowly move out, the same thing if we could automate, it is manual and semi-automatic can be done. If it is more quantity, lesser variety, then we go for dedicated measuring machines. Okay. And here machine vision is also exhaustively used. Then when we move to the large product variety and quantities are very minimum, we use coordinate measuring machine. Coordinate measuring machine is assisted by a computer. So, it is computer controlled coordinate measuring machine, wherein which flexibility is more, quantity is less. Then we have two more boxes. So, one is which is for batch production. We will use flexible inspection system. We will see what is flexible inspection system later, and here it is motorized control. It will not be computer control, but motorized control. So, it is predominantly by using a joystick. So, this and this, there will be a small overlap in the instrumentation part of it. So, this is a PQ chart for inspection technology, which this is very important for you to understand when we talk about SIMS environment, which equipment to choose and what should be the level of automation in the factory. When we talk about group technology leading to a cell, that means to say a manufacturing cell, we will have machines, we will have material handling devices, we will have assembly / inspection. So, inspection we have to think which machine to use and what should be the level of automation. So, the conventional measuring and gauging techniques. Measuring instruments provide a quantitative value of the part feature of interest. For example, steel ruler, caliper, micrometer, dial indicator, protractor, all these equipments provide a quantitative value of the part feature of interest. Next is gauging techniques. In gauges, what we determines whether a part feature falls within a certain acceptable range. So, it will not be absolute, I told you, no. So, suppose if it is 6 plus or minus 1 millimeter, you will try to have a gauge which measures from 5.9 to 6.1 millimeter. So, within that it will only say yes, go, no go, that is all. So, gauge is more of comparison measurement. So, determines whether a part feature falls within a certain acceptable range. Example, snap gauge for external dimensions, plug gauge for internal dimensions, thread gauges, and then we also have slip gauge. All these things are used for comparison and then we try to develop. So, these are the conventional measuring device and gauging techniques. When we talk about coordinate measurement, so these two, if you go to P to Q chart, it is more of manual assisted measuring. When we talk about coordinate measurement, concerned with a measurement of the actual shape and dimensions of an object and comparing these with the desired shape and dimensions specified on a part drawing. So, what is that? You have developed a part drawing, you have used it for machining, and now the same part drawing is used for inspection. Now, in inspection what it does is it compares with what is given in the part drawing and what is the deviation. Okay. To do this, we will use coordinate measuring machine. When I say coordinates, x coordinate, y coordinate, z coordinate, r coordinate and theta coordinates are generally used. This is for Cartesian and this is for polar. So, you can use both or a combination of these two can be used for measuring. Coordinate measuring machine, an electromechanical system designed to perform coordinate metrology. In a part drawing, when you draw it in a 3-dimensional view, all you have is x, y and z coordinates. So, while measuring we give the same x, y, z coordinates. A CMM consists of a contact probe that can be positioned in 3D space relative to work part feature, and the x, y, z coordinates can be displayed and recorded to obtain dimensional data about the geometry. So, dimensional data is nothing but the x, y, z data. So, this is a typical coordinate measuring machine. The interesting part of this measurement is you can have one point as reference for the entire object. For example, if you try to use a vernier caliper and a dial gauge and other measurements, it is very difficult for you to measure with respect to one reference and give the data. But in CMM, it has a one point reference. You put a calibration dial, you calibrate it, and then that you make it as world coordinate system 0 0, then you transform the user coordinate system, measure it on the part and then report it. So, coordinate measuring machine is an instrument which is exhaustively used in a SIMS environment. So, the data is attached to a computer, the computer gives data, records data and finally generates the deviation chart for features. All can be done by a computer. So, what are all the components of a CMM? CMM is a flexible measuring device capable of providing a highly accurate dimensional position along 3 mutual perpendicular axes. Highly precision mechanical structure, these are the components, probing system, machine control unit and the software. So, these two are very important. These two are of course software more oriented. The optional components on many CMM are drive system and control units to move each axis like a pendant given, a digital computer system with application software. What are all the elements of a CMM? You will have a precision machine structure. This leads to a coordinate measuring machine. You will have machine control unit computer, then you have a CMM software, then you will have a probing system. So, this is how a CMM works. So, here is a part. So, this is a probe. So, this is the structure what moves, this is the structure, and here whatever you have, this is the probe, and then this is the world coordinate system and here you will have a user coordinate system, and here the probe touches the workpiece, and where are you see a dot points, these are all the points. Suppose you want to take a plane, so it touches 6 points and it tries to generate a plane surface. So, these are the points, the data points are taken, and then the data is now using the help of a computer, and then we try to get the data. You can see world coordinate system x, y, z, and then you see how does this coordinate system changes, so that they get all the data on these different types of surfaces. You see here it is transformed, so it is rotated and then you try to get it. So, you can transform with respect to this probe or with respect to the workpiece. Okay, so, I would prefer that you can put it to the workpiece itself. User coordinate system can be world coordinate system transformed to user coordinate system, and then you try to get the output. So, the most critical part is the structure, wherein which the resolutions, all these resolutions, repeatability, reliability, precision, all these things are taken care. But the heart of the CMM comes from the probe. So, a probe has a spindle to hold the probe. This is the probe. This is the probe head and this is the probe. So, the tip of the probe is always circular in nature. Why? Because you can get a point contact, or if you have a dot there, though it might get worn and torn. So, it is always better to put a circular one, so you get a point data. So, circular is very useful when you have a perpendicular surface, when you have an angled surface, so it can try to measure. So, this round is a sapphire ball, alumina ball or a ruby ball which is used. It is highly polished and it is placed at the tip. So, this is the stem is very sensitive. So, any touch it can quickly detect and then do it. You can have a single probe, you can have something like a star probe. So, star probe, if you have a hole to be measured. So, now if you use a single probe, it is going to take time. So, what you do is you try to do the depth and simultaneously move along the sides to get what is the width or what is the diameter of the hole and the depth of the hole. So, for this we use a star type probes. So, there are several configurations, I have just put only 2 for your understanding. So, this is a touch single probe touch base, wherein which it touches the gear at several points. If you look at it, the points, who decided the points have been decided from the part drawing, and not all the features will be measured, only critical features will be measured such that it will make sure the quality of the gear is good. So, this is the probe head, and this is a gear. Very interesting. So, and it is all done automatic, by the way. You can do it manual by a teach pendant, what we studied in robo. We can also have a teach pendant, or we can write a program to do, or we can manually operate by a pendant which is there. So, this CMM works on programmable type, all the 3 options are open. So, the mechanical systems, there are 6 common types of CMM mechanical structures. There are 6 types. So, cantilever, moving bridge. Why is this? This is like a robo, what we studied body and arms, same way we are studying here. Structures, cantilever type, moving bridge type, fixed bridge type, horizontal arm, gantry type and column type. You have to choose depending upon your size, shape of a component, you have to choose a structure, because this structure is going to decide the resolution, repeatability, reliability, precision of your system. So, this is a typical cantilever type, this is a cantilever type. Okay. So, there is a overhang and there is one more overhang, then you have a stylus which touches and then you try to get the output. So, if there is a error in this stylus, it is transferred to this, and so naturally the error data whatever you measure is going to be tricky to handle. So, first we do calibration, if at all there is a sag, we try to remove it and then get it done. So, the next one is going to be moving bridge. So, this is moving along. So, suppose you have a car here, large component, a car here. or a rocket part which is a larger diameter, you can place it here and the gantry moves, slides along the x direction, and then you try to get the data. The advantage of this moving bridge as compared to that of cantilever is, if there is a error which is happening in the x axis, that will be carried to y axis and z axis value. Here what happens, it will be removed to a large extent. If there is a error in the x axis, you can nullify it after measuring with y and z. So, it will not be carried. So, the third one you can have is fixed gantry, but a moving table. The next one is horizontal arm. So, the difference between the horizontal arm and the cantilever type is, there is a horizontal and then there is a vertical. Here there is only horizontal. So, if you have a large component and if it is along a plane and you want to measure it along the vertical axis, then we use this horizontal arm. Then you have a gantry type which is used, and then finally it is also a column type. These are the 6 common CMM structures which are exhaustively used in the factory environment. So, thank you.